Hello, and welcome to an introduction to antennas with a focus on mobile applications presented by STI-CO Industries. In today's class, we're going to be covering some common antenna terms and why they matter, choosing the correct cable, and vehicle installation considerations. A transmission system is comprised of three basic elements: the transmitter or receiver, the transmission line, and the antenna. To work correctly, these three items need to work together so that the maximum amount of energy possible is radiated in the proper direction. That is to say, each of these must match the other, otherwise we encounter losses in the system, and that energy that we want to use for increased range is wasted in the form of heat or radiated in a non-useful direction. The radio manufacturers provide you with all sorts of data as to how their equipment will perform, including power, number of channels, weight, etc. The feedline manufacturers will list specifications on loss versus frequency, durability, characteristic impedance, and so forth. But how do you determine what constitutes a good antenna? You can have a high power radio and low loss, high quality feedline, but if your antenna isn't designed to work for your application, the results could be reduced range, equipment damage, and unhappy operators. So today we're going to discuss what characterizes a good antenna, and then we will explain what compromises we have to make for mobile systems. Antennas may look static, but when transmitting, they are filling the surrounding area with electromagnetic radiation. Shown here is a side view of a dipole antenna. Notice that the entire volume is filled with EM radiation as it pushes energy out into the atmosphere. One takeaway from this is that how you install an antenna and what's located in the near field or immediately around the antenna is just as important as the type of antenna that you select. Because we are dealing with signals traveling through free space, there are things that are going to impact our antenna's performance that are beyond our control. There are obstructions such as buildings, other vehicles, terrain, hills, trees, weather, ice, snow, and rain can impact our performance, and of course interference from other transmission sources. That's why it's so important to optimize our antenna for our application so that we can get the best performance out of the system as possible. Let's begin our terminology breakdown with frequency range. Expressed in hertz, frequency is the number of cycles per second. Normally, for transmission systems, we're going to be dealing with megahertz or higher, such as gigahertz. For antennas, we need to know the lowest and the highest frequency required by the transceiver. For certain licensed frequencies, this may be within the range of the possible operation of the transceiver itself. For multiband systems, it is important to note all the different bands that the transceiver may operate within and the number of ports associated with those frequency ranges. Input impedance. Impedance is a measure of resistance and reactance. What is important for you to remember is that in general, today's transmission systems are designed to work at 50 ohms. The transmitter, the feed line, and the antenna should all work together. If the impedance of any of these three things is different, the result is loss in the form of heat or reflections. VSWR, or voltage standing wave ratio. When you key the microphone of your transmitter, your voice is converted into an electromagnetic wave at a specific frequency. This wave is confined to the feed line and transferred to the antenna. Ideally, all of the energy in that wave would be advanced into the antenna and radiated into space. In reality, however, some of this energy is reflected back into the feed line towards the transmitter, which you would be able to measure as reflected power. In order to quantify how much energy is reflected back into the system from the antenna, we use the term voltage standing wave ratio, or VSWR. For our purposes, the lower the VSWR, the better your system is. The ratio of forward power to reflected power is related to VSWR. For our reference, 100 watts forward with 11 watts reflected would yield a VSWR of approximately 2 to 1, which is considered the top limit for transmit systems. When evaluating VSWR published by antenna manufacturers, always note the method in which they attain their measurements, as this is often idealized and may not match your specific application. Power handling capability is a description of how much forward power an antenna will be able to handle. Measured in watts, this is continuous power that the antenna should be able to handle in a normal application. Always be sure to check that the antenna that you are considering meets or exceeds the radio power of your system. The antenna pattern is a 3D representation of the amount of energy directed along the horizon from an antenna. Notice in this example of a quarter wave how the energy radiates out equally in all directions. This is called an omnidirectional pattern. An omnidirectional antenna is desired for mobile applications, since you never know the direction of your transceiver antennas that are going to be receiving the signal. While a 3D representation of the antenna pattern is nice, a more common presentation is shown here. Notice here that we have the azimuth, which would be like looking at the antenna from the top. Notice that this is an omnidirectional pattern, as shown in the previous example. A second representation would be the elevation, which would be like taking a slice and looking at the antenna from the side, showing the lobes of the antenna and how much energy focuses in on the horizon. Notice for both of these, they are frequency dependent, so always note the frequency and you should get a sampling across the operational bandwidth of the antenna. Gain is a measure of the amount of energy directed along the horizon for an antenna. By manipulating the shape of an antenna relative to its frequency, we can focus more and more energy along the horizon. Notice in this example where we show a quarter wave antenna, which is a classic design, a half wave antenna, and a 5/8 wave antenna. As we progress from quarter to half to 5/8, you see more energy directed along the horizon. Now you may ask, why don't we simply incorporate more gain into all antenna designs? Well, there are trade-offs as we do this. As we increase the gain, we tend to lose bandwidth as a function. Also, the physical size of the antenna increases, making it much larger, and for certain applications, this simply won't work. You need to evaluate how much you need gain for your application and evaluate the trade-offs. Polarization of an antenna is how the waves radiate away from the source. Whether by design or physical orientation, just note that the polarization of your receiver system should match that of the transmission system. In other words, if your mobile antenna is vertically polarized, the receiver system that you're operating into should also be vertically polarized. If you use two different types of systems, for example, horizontal and vertical, you will begin to incur loss. Note some of the misalignment degrades that you're going to see in the following slide. Misaligned by 45 degrees, and you can see 3 dB of signal loss. Misaligned by 90 degrees, and the loss could be 20 dB or more. For inline components such as cable, filters, or other items, one thing to examine is insertion loss. Expressed in decibels, insertion loss is the amount of power lost due to heat or unintended radiation. One thing of note is to keep the insertion loss of any item you add to the system as low as possible. Reduce cable length when possible, or look for low loss alternatives. Also, when evaluating two-port devices, such as filters, look for a lower insertion loss, both average and max, whenever possible. One thing to note about insertion loss is that it's frequency dependent. Here we have an attenuation calculator. Everything is maintained the same between top and the bottom calculation. Both use RG58, both are 25-foot runs, but all we varied between the top run and the bottom is the frequency. Notice at 155 megahertz, the total run attenuation is 1.4 dB. But when we increase the frequency to 2400 megahertz, the attenuation goes to 6.2 dB. So simply varying the frequency, you will incur higher losses within the cable. As a general rule, for higher frequencies, a higher quality, lower loss cable is recommended, especially when the lengths have to be longer. Finally, we'd like to discuss the different locations for installing antennas on a vehicle. We've broken these areas up into 3 different sections. Green, the best place for install and operation. Yellow, a compromised location where it's easy for install but may have possible radiating issues. And red, not the best place for antenna operation and a more complicated install. Let's begin with the green zone, or the vehicle roof. This area is typically the best location for antenna installation. It's generally free of obstructions, allowing for omnidirectional operation. The antenna is close to vertical, which is typical for most receiving systems, and is easy to access, allowing for a simple installation and routing of the cables. Here we have a simulation showing an antenna radiating on top of a vehicle roof. You can make out the outline of the vehicle in the center of the slide. Notice how the energy moves away from the antenna evenly in all directions. Now let's review the yellow zone. In this zone, you have some obstructions. However, it's still typically easy to install the antenna, but you will get some directionality. These types of antennas may be on-glass or in-glass antennas, or fender-mounted antennas. Here's the radiation characteristic of an internally mounted antenna in a vehicle. Notice here the red sections inside the vehicle as energy is re-reflected inside before it makes it out through the windows in the glass. This is why you'll get some directionality out of this type of an antenna setup. Finally, we come to the red zone. This is the lowest point in the vehicle, and is typically where we would install panel type antennas, bumper type antennas, or bump step antennas. The installation is a little more difficult and usually requires 2 antennas across the vehicle to attain omnidirectional operation. In review, today we've covered common antenna terms and how they could apply to sourcing a good antenna, choosing the correct cable for your application, and vehicle installation considerations. Thank you for your participation today. Hopefully you'll find this information helpful in sourcing your next antenna. If you would like more information, please visit our website at www.STI-CO.com or contact us at the information provided below. Thank you.